When performing a service calculation, do not assume the lighting load to be at 125%. According to National Electrical Code Section 220.11 and Table 220.11, branch lighting circuits are calculated at 125% of the connected load to account for potential overloads. However, service size calculations use lighting load demand factors. These are at 100%, meaning there is no additional allowance for overloads. The reasoning is that the 125% demand factor for branch lighting circuits is intended to minimize voltage drop and prevent nuisance tripping of circuit breakers during peak lighting loads. When calculating the service size, it is assumed that not all lighting fixtures will be operating at full load simultaneously. The 100% demand factor for lighting in service calculations accounts for this expected variability in lighting loads. Therefore, when sizing service feeders, you should use the following demand factors for lighting. For a main service over 100 kilowatts, use 100% of connected load. For a main service 100 kilowatts and below, use 50% of connected load. This ensures that the service size is adequate to handle the anticipated lighting loads without oversizing the feeder unnecessarily. Let's delve into the specifics of how to calculate service and feeder sizes according to the National Electrical Code, or NEC, focusing on lighting loads and demand factors. The goal is to ensure that electrical systems are safely and efficiently sized to handle anticipated loads, preventing both undersizing, which can lead to overloads and hazards, and oversizing, which can be wasteful and costly. We will cover the steps involved in calculating these loads, the relevant NEC sections, and practical examples to illustrate the process. Firstly, branch circuits are calculated at 125% of the continuous load plus 100% of the non-continuous load. This 125% factor for continuous loads on branch circuits ensures that the wiring and overcurrent protection devices are adequately sized to handle loads that operate for 3 hours or more at a time. This precaution helps to prevent overheating and potential fire hazards. Secondly, for service calculations, the process involves several steps, starting with determining the total connected load. Begin by identifying all the loads that will be connected to the electrical system. This includes lighting, receptacles, appliances, motors, and any other electrical equipment. For each load, determine its volt-ampere rating or wattage. If the load is rated in watts, divide by the voltage to obtain the amperage and then multiply by the voltage to get the volt-ampere rating. Thirdly, apply demand factors to lighting loads based on NEC Table 220.42. Demand factors allow for the fact that not all loads will be operating at their maximum rating simultaneously. This table provides specific demand factors for different types of occupancies and lighting loads. For example, a demand factor of 100% might be applied to the first 3 kilowatts of lighting load in a dwelling unit, with a lower percentage applied to the remaining load. Demand factors for general lighting vary depending on the occupancy and the size of the load. For dwelling units, the NEC provides specific guidelines for calculating the lighting load based on the square footage of the dwelling. For non-dwelling units, the lighting load is calculated based on the volt-ampere per square foot requirement specified in NEC Table 220.12. After calculating the total lighting load, you can apply the appropriate demand factors from NEC Table 220.42 to determine the actual demand. Fourthly, calculate the receptacle loads according to NEC 220.49. For dwelling units, each receptacle outlet is typically calculated at 180 volt-ampere. For non-dwelling units, the receptacle load is calculated based on the volt-ampere per square foot requirement specified in NEC Table 220.12 with a minimum of 180 volt-ampere per outlet. Demand factors may also be applied to receptacle loads in certain situations, as outlined in NEC 220.44. Fifthly, calculate the appliance loads. Determine the volt-ampere rating of all appliances that will be connected to the electrical system. For household cooking appliances, the NEC provides specific demand factors in Table 220.55, which take into account the diversity of appliance usage. For other appliances, the load is typically calculated at 100% of the rating unless demand factors are permitted by the NEC. Sixthly, calculate the motor loads according to NEC 430.22 and 430.24. Motor loads are calculated based on the horsepower rating of the motors and the corresponding full load current ratings listed in NEC tables. The largest motor load is calculated at 125% of its full load current, with the remaining motor loads calculated at 100%. Demand factors may also be applied to motor loads in certain situations, such as when multiple motors are unlikely to operate simultaneously. Seventhly, add all the loads together. Once you have calculated all the individual loads and applied any applicable demand factors, add them together to determine the total calculated load. This is the load that will be used to size the service entrance conductors and overcurrent protection devices. Eighthly, determine the service entrance conductor size. Based on the total calculated load, determine the appropriate size of the service entrance conductors using NEC Table 310.16. This table provides the allowable ampacities of conductors based on their size, insulation type, and installation conditions. Be sure to select conductors with an ampacity that is equal to or greater than the total calculated load. Ninthly, select the overcurrent protection device. The overcurrent protection device, typically a circuit breaker or fuses, must be sized to protect the service entrance conductors from overloads and short circuits. The NEC provides specific requirements for sizing overcurrent protection devices in section 240.4. In general, the overcurrent protection device should have an ampacity that is equal to or less than the ampacity of the service entrance conductors. The 100% versus 125% rule is a critical distinction in electrical calculations, particularly when it comes to continuous loads. The NEC defines a continuous load as one that operates at its maximum current for 3 hours or more. This distinction is important because continuous loads can cause conductors and overcurrent protection devices to overheat if they are not properly sized. For continuous loads, the NEC requires that the overcurrent protection device be rated at not less than 125% of the continuous load. This means that if you have a continuous load of 20 amps, the overcurrent protection device must be rated at least 25 amps. Similarly, the conductor supplying a continuous load must be sized to carry not less than 125% of the continuous load. This ensures that the conductors can handle the heat generated by the continuous load without overheating. For non-continuous loads, the overcurrent protection device and conductors can be sized at 100% of the load. However, it is always a good practice to oversize conductors slightly to allow for future expansion and to reduce voltage drop. Understanding and applying demand factors correctly is essential for accurate service and feeder calculations. Demand factors are based on the principle that not all loads will be operating at their maximum rating simultaneously. By applying demand factors, you can reduce the calculated load, which can result in smaller conductor sizes and lower equipment costs. The NEC provides specific demand factors for various types of loads, including lighting, receptacles, appliances, and motors. These demand factors are based on historical data and statistical analysis of load profiles. Some common examples of demand factors include, firstly, lighting loads in dwelling units where the demand factor decreases as the square footage of the dwelling increases. Secondly, receptacle loads in office buildings where the demand factor decreases as the number of receptacles increases. Thirdly, appliance loads in dwelling units where the demand factor varies depending on the type and number of appliances. Fourthly, motor loads where the demand factor decreases as the number of motors increases. When applying demand factors, it is important to follow the NEC guidelines carefully and to use the appropriate demand factors for the specific type of load and occupancy. Using the wrong demand factors can result in undersized conductors and overcurrent protection devices, which can create a safety hazard. Here's an example of calculating the service size for a small commercial building. Firstly, determine the connected load. Lighting 5000 volt ampere, receptacles 3000 volt ampere, HVAC 10,000 volt ampere. Secondly, apply demand factors. Lighting 5000 volt ampere times 0.8 equals 4000 volt ampere. Receptacles 3000 volt ampere times 0.7 equals 2100 volt ampere. HVAC 10,000 volt ampere times 1.0 equals 10,000 volt ampere. Thirdly, calculate the total demand load. 4000 volt ampere plus 2100 volt ampere plus 10,000 volt ampere equals 16,100 volt ampere. Fourthly, determine the service size. Assuming a 208/120 volt three-phase system, the service amperage is 16,100 volt ampere divided by 208 volts divided by 1.732, which equals 44.7 amps. Therefore, a 60 amp service would be adequate. Another example is calculating the feeder size for a dwelling unit. Firstly, determine the connected load. Lighting 1500 volt ampere, small appliance circuits 3000 volt ampere, laundry circuit 1500 volt ampere, electric range 8000 volt ampere. Secondly, apply demand factors. Lighting 1500 volt ampere times 1.0 equals 1500 volt ampere, small appliance circuits 3000 volt ampere times 1.0 equals 3000 volt ampere. Laundry circuit 1500 volt ampere times 1.0 equals 1500 volt ampere. Electric range 8000 volt ampere times 0.7 equals 5600 volt ampere. Thirdly, calculate the total demand load. 1500 volt ampere plus 3000 volt ampere plus 1500 volt ampere plus 5600 volt ampere equals 11,600 volt ampere. Fourthly, determine the feeder size. Assuming a 240/120 volt single-phase system, the feeder amperage is 11,600 volt ampere divided by 240 volts, which equals 48.3 amps. Therefore, a 60 amp feeder would be adequate. Now we will cover common mistakes to avoid, including failing to account for continuous loads. One of the most common mistakes is failing to account for continuous loads when sizing conductors and overcurrent protection devices. Remember that continuous loads must be calculated at 125% of their maximum current. Another common mistake is using incorrect demand factors. It is essential to use the appropriate demand factors for the specific type of load and occupancy. Using the wrong demand factors can result in undersized conductors and overcurrent protection devices. Another mistake is overlooking voltage drop. Voltage drop can occur when conductors are too small or when the distance between the source and the load is too long. This can cause equipment to malfunction and can also create a safety hazard. To minimize voltage drop, it is important to select conductors that are adequately sized for the load and the distance. Lastly, ignoring future expansion is a common mistake. It is always a good practice to oversize conductors and equipment slightly to allow for future expansion. This can save time and money in the long run by avoiding the need to replace undersized components later on. To ensure compliance with the NEC and to avoid common mistakes, it is recommended that you consult with a qualified electrical engineer or electrician. These professionals have the knowledge and experience to perform accurate service and feeder calculations and to ensure that electrical systems are safely and efficiently sized. In addition to consulting with professionals, it is also important to stay up to date on the latest NEC requirements. The NEC is updated every 3 years, and it is essential to be aware of any changes that may affect your electrical designs and installations. There are many resources available to help you stay informed about the NEC, including seminars, workshops, and online training courses. By following these guidelines and best practices, you can ensure that your electrical systems are safely and efficiently sized to handle anticipated loads, while also minimizing costs and maximizing performance. Always prioritize safety and compliance with the NEC to protect people and property from electrical hazards.